All right, guys, in this video, we are going to cover section 3.3, and this is just modeling with exponentials. So now that we have learned a lot about them, we need to talk about how can you actually relate them to the world a little bit more than what we've done. So a pretty common model that we can use with exponentials is maybe a model that is talking about population. Now, this does not just apply to population as in like people. So we are going to talk about that as well in other ways that it can be used. But this is a pretty relevant model to a lot of different types of exponential situations. So in this equation, what you're seeing is just they're saying the population is the initial population, right? P0 is the initial population times, and then we have 1 plus the rate. So they will talk about either like an increasing rate or a decreasing rate, the rate at which the population changes, right? But it's changing it into a decimal. So a lot of times they'll give it to you as a percent. You just want to make sure that you convert it to a decimal first, and then you can plug it in. If you are increasing, you will add that rate. And if you are decreasing, your rate will be a negative. So you would be subtracting. So just look out for that. And then we have this exponent. Now, this exponent we can kind of fiddle with sometimes depending on the scenario. In this scenario, it would be time in years. However, you can talk about population or different things changing in different times as well. So, but typically, we're going to be seeing this in years, especially if you're talking about like population. They usually do that in years. Okay, example 1. They said determine the exponential function with an initial value of 12 increasing at a rate of 8% per year. So we're just going to practice plugging in the values for that type of function. So here we said the initial value is 12. Now that's your P0, right? So this is P sub 0. They said, what else? The rate is 8%. So if R is 8%, then as a decimal, all we have to do is divide that by 100 or just scoot your decimal place over. This is 0.08. So we'll be using that. So that should be enough to be able to write my population equation. So this is P of X equals, and we're going to put our initial, which was 12. This is 1 plus my rate, which was 0.08. And we're going to say this is to the x power. Okay, if I do it P of X, if I did P of T, I would use a T. It doesn't really matter what letter I use. All right, one more thing just to make this as clean as possible is go ahead and add the numbers that are in the parentheses. So this is 1.08. And that would be a nice little equation to model that scenario. Okay? So next one we have is, what about a bacteria growth? Well, bacteria growth is kind of like population growth. So we are able to use that same equation. However, there's going to be something a little bit different about the time. So I want you to see what the units are in here. They said that our culture of 100 bacteria is put in a petri dish and doubles every hour. So kind of my model should be working about like my time being hours rather than years, because they're telling me that it doubles every hour. That's the rate. Okay. The last one, the rate was 8% per year. This one, the rate is doubles every hour. So my variable X or T or whatever, that time is going to be hours instead of years. It says, when will the bacteria reach 350,000, right? So we're going to do the same situation. Now this one's going to be a little bit more interesting because they are not just asking for the equation, but that is where we need to start. So I'm going to do the same thing. I'm going to plug into that formula. I'm going to call this B for bacteria. It doesn't really matter what we call it. I'm going to call it B for bacteria, and I'm going to let my variable for time, I'm going to let that be H for hours. Again, you can use whatever letters make sense to you. It doesn't really matter. Okay. Okay, so we're going to plug in our initial amount, which was 100. And then we're going to have 1 plus. Now our rate, it says doubles every hour. So I want you to think about what that is as a percentage, right? Doubles every hour means that every hour it's going to become twice as big, or you can think of it as saying that's like 100%, right? If something was 2, then doubling that becomes 4. So that was 100% growth in that hour. So you could say this is 100%, which as a decimal is just 1. You could say 0.00 if you wanted, but that's what I'm going to use for my rate. And then this would be to the h power, right? I'm going to clean this up just a little. 100. This is 2 to the h. And this might make more sense even if you had jumped to this place, because doubles every hour, right? Times 2 every hour. That might make more sense even just to jump to that moment. Okay, now we're going to solve this. They said we want to know, when is the bacteria going to reach 350,000? So 350,000. And we do have a nice way to solve for this, but we haven't reviewed it yet this year. They involve logarithms. So what we're going to do for the time being until we get to where we've reviewed those is we are going to solve this by a graph. However, we will eventually get to the point where we are solving it another way. So what I'm going to do in my calculator is I'm going to put this on one side. So the 350, 1, 2, 3, okay, 350,000. And then on the other one, I'm going to put the right side of the equation. Oops. Just like that. And now I'm going to go up and I'm going to see where they intersect. And so this graph right here doesn't show me a whole lot. I'm going to put this on auto, see if that helps a little bit. I can see the 350,000 line. I can see the exponential down here, but I don't see where they cross, which means I should move over here. And I can see that they cross right there. Now, I would not eyeball this. This thing is not wanting to land exactly on their intersection. So what I would do is go up to the calculate. Either one of the equations is fine, but we're going to find the intersection. And then that x value is what we want. Okay, that is 11.773. So we're going to say here with our hours, it's about 11.773. So what we did is we just put that in the grapher and we saw where they intersected, right? Now, here's the deal. We could answer it like this if they just wanted to know like how many hours, but a lot of times when we think about time, we don't think of 11 hours 0.77. You know what I mean? Like we don't think of it that way. What we do is we think of like hours and minutes. So what I do know here is that this is 11 hours, but how many minutes is that? So here's a way you can find it. I can make a proportion. Okay, that was out to the thousandths place. So I can say 773,000 equals what out of 60, since there's 60 minutes in an hour. And if you solve this proportion, it tells you about how many minutes it was. So I can cross multiply, gives me 1,000x. 773 times 60 is 46380. And that puts my x right here at about 46 minutes. So I'm going to say in 46 minutes. That just makes a little bit more sense to the average reader, somebody who's reading your data. Okay? All right. Next thing, we're going to talk about decay and half-life. So radioactive decay, when things are radioactive, they eventually, over time, become not radioactive. So with that being the case, there's something that we call radioactive decay, where the atoms are going to change from a radioactive state to a non-radioactive state. It takes a long time, but it does happen. A half-life is the time it takes for half of a substance to change its state. So if you're talking about like the half-life of some radioactive material, it's the time it takes for half of that material to become non-radioactive. Okay. So it doesn't just work with radioactivity. It can work with different types of decay. But so whenever they talk about half-life, what they're talking about there is the time that it takes for the substance to change its state for half of the substance in the study. Example 3 says the half-life of a substance is 20 days, and its mass was 5 grams initially. When will there be 1 gram remaining? All right, so we need to think about what this is all telling us here, okay? We know that the initial amount, I'm just going to call this f of x for my study here. I'm going to let that be my initial amount was 5. We want 1, and then we need to think about what the rate is. If it is the half-life, right, then that is something that goes along with decay. All right, so that's something that we want to kind of think of is it goes along the same lines as decay. So I would maybe make even a note up here that goes with decay models, okay? But we're looking at it to change, and we want it to change half of its stuff, right? So when we look at that rate, we're looking at this is 50% that's going to change for a half-life, which means that my rate would be about 0.5 as a decimal. Since it's decay, we're going to subtract 0.5. Okay, but that's where we're kind of getting here. Then we want to look at my time up here. Now, I want you to think about this, okay? Remember my original model, we said that the time was in years. Then the next problem we had this talking about time in hours. This one is neither one. This is talking about the half-life. The time it takes to do this, to be cut in half, is 20 days. Okay, so we're looking at what out of 20? Because 20 days is the time span that it takes for it to cut in half. And I want to know how many days will we be at when there's 1 gram remaining. Okay. All right, so from there, let's clean this up just a teeny tiny bit. We got f of x equals 5 times, this is 0.5 x out of 20. And then we're able to solve. They said, when will there be 1 gram remaining? We'll replace that with a 1. And we need to solve for that x value. Okay, so from there, we're going to do the same thing we did on the last problem, and we're going to type these in. So I'm just going to go up and edit the 2 equations that we have. I'm going to change this to just be a 1. And then this guy is going to be a 0.5. 5, and that exponent needs to change as well. I'm going to go to the auto, and again, I'm not seeing where they intersect, so I'm going to scoot this thing over until, it looks like I see them intersect, so it looks like it's over in here. I'm going to go to the calculate and have it find that intersection for me. Let me make sure everything's in there right. Yeah, okay, find intersection, and it says 46.439-ish. So we're going to say x is about 46.439-ish, okay? Now, that's in days, right? So remember how earlier with time we were like, well, normally we don't measure days in like 46.439. Like we'd say it was 46 days, and then we would think of like hours, right? So how many hours is this representing? So we're going to do the same thing we did before, make a little proportion. There are 24 hours in a day, so make sure to use that. We're going to cross multiply. That's equal to 10536. And so this value is going to be about 10 and a half hours. Now, sometimes, that we could say 10 hours and then 30 minutes. We could even do that. We could say 10 hours, 30 minutes. That would be fine. So there's a lot of different ways that you can kind of give that answer. Kind of depends on how it's wanted. But usually when you write something like this, you would you wouldn't just say 439 days. You would just say 46 days, 10 hours, or even 10 and a half hours would have been fine. Okay. All right. One more topic real quick, and then we'll be done. So we're going to talk about regression for just a second. Regression is a nice little way for if you get a table, especially if the table is not exactly perfect, you can get a good idea for a model. So I'm going to say, I want y'all to get these notes copied down real quick that you see up on the screen. Different calculators are going to work different, so I tried to make them kind of generic. On our calculator that we're going to use in here, there is a whole regression menu. So if you see over here, you've got your calculate, grapher. Directly under grapher, there is a regression app. Okay, and that's what we're going to go to on our calculators. Now, if you're using a TI-84, you may have to input lists, and that's a little bit different. But however your calculator wants you to do it, input your data. Okay, and then we're going to use the regression, and we want the one for exponentials where it's y equals a times b to the x. It'll give you an a and a b value for your equation, and you'll be able to use that to represent your data. So I'm going to show you on example 4 how this is going to work. We're going to go to the regression menu, and we're going to put in our table of values. So I'm going to put my x's and then put my f of x's. Okay, 0, 3. Okay. Let me make sure I typed it in correct. Okay. Once you have all that in, I'm going to zoom in just a little so y'all can see this a little bit better. Once you get that data in, what the question had said is to use the regression model, and then we're going to predict a value. So I'm going to give an equation. Okay, now I can't really give an equation from this screen, but we can go over to like the little grapher option, and you're going to see all those points plotted. You can go around and see all the points that you plotted, okay, on that list. And we're going to go up to the regression option. So I'm going to go up here, regression, and we're going to select the correct one. So there's 2 different exponential ones. Be careful that you pick the right one. One of them works with the E in it. We're not going to go with that one. We want this one where it says A times B to the X. Okay. All right. Now you can either just move your cursor down and it pops up your equation like this. You also can go back up to this regression menu and it writes it out right there as well. Okay. So there's 2 different ways that you can go at it. But my equation here, I'm going to write this over here on the paper. It was y equals 2. It says 24998. I'm going to round that to be about 2.25-ish. And then we have times, this is 1.16. And then this is to the x power, just like that, okay? And they said predict f of 15. So what we're going to do is plug in a 15. We're going to do 2.25 1.16 to the 15th power. And y'all, if you type that in, you end up with the nice, lovely number. Hold on, I've got it written down. Okay, it's about 20.847. Okay? So that's a really nice, easy way to get an equation from a list and use that to your advantage. Okay, it's also possible, I just didn't want to waste too much time, but it is possible to get a logistic function, and the logistic functions, they are going to give you like a max sustainable population. So you'll look for those words, and then you would use a logistic model instead. That max population is the limit to growth, so the top number from a logistic function. So just look out for that, okay? All right, y'all, that is it for this lesson, and I will see y'all in the next one. Bye.